Welcome. I'm going to give you a short presentation on our simulation use case 1. I want to go over this poster today to describe to you the simulation itself and also the technical details behind this presentation, how we built it up. So in the poster we can see on the top that our goal was to simulate a traffic simulation based on a closed loop simulation where a lot of vehicles interact with each other, and we even have a fairly complicated map that we selected for the simulation to have a very nice and complicated simulation to demonstrate all the results that have been achieved within the set-level project and brought to execution within this and other simulations. On the right side, we can see how the map looks. We have 4 arms of this crossing, fairly large arms, large crossing here with a lot of lanes coming in and leading out of this crossing. We can also see that there is a lot of different vehicles driving around in this map, in this scenario. The main vehicle or the vehicle under interest is this white vehicle here that is controlled by a highly automated driving function, just because we wanted to have also a highly automated driving function driving into the crossing, turning left, and then leaving to the top. Here we also have to consider that we have oncoming traffic, which of course has right of way in that case, so the white vehicle has to stop and let the traffic pass before starting to turn. Also, we can see that there is this small P circles with a yellow circle. These are pedestrians that are moving and that are actually crossing the northern arm of this map, and therefore also here we expect interaction to happen between our white vehicle and the pedestrians. And to make it even more interesting, we placed further vehicles down here and up there, as well as pedestrians all over the map that will move around this scenario throughout the simulation. Now that was our basic setup that we came up with for the simulation use case. And of course we needed a lot of models to build this up. These models have been developed within the set-level project, have been provided to us for integration and execution of the simulation. Now that was the part when the technical work started. The technical details are shown in this image in the middle on the left side. We see the technical architecture that we came up with for the simulation. It is strictly following the generic architecture that has been developed within the set-level project. And in this case, we can see that the different models for pedestrians, for vehicles that are controlled by drivers, but also for the automated driving function, which is shown here on top, is incorporated here based on the FMI standard, as the models are wrapped as FMUs. Models interact with each other by sending data based on OSI messages back and forth, and that's also how everything is coupled to the simulation core. In our case, this was OpenPath, which is an open source tool. The white box actually also indicates the group of components or simulation models that have been coupled with each other based on the SSP standard, a system structure and parameterization standard that allows to define networks based on multiple FMUs, as we have coupled them in here. This box would allow to execute a single simulation, but we wanted to execute an analysis case where we have to do multiple simulations. That's why it is embedded in a larger framework called a platform in our case, where on top we have some analysis task as an input. And to execute this analysis task, we especially have to apply stochastic variation to the scenario. This is done here by the concrete scenario generator and the scenario manager, which are responsible to apply parameter variation and come up with hundreds and thousands of different scenarios based on a first logical scenario as we have seen it before. And we can run the simulation for each one of those cases. And afterwards, we apply some post-processing, some result compilation in order to obtain insights in statistical evaluations over all the different simulations that we did. And we can especially identify the simulations that are critical, which is our main interest in this simulation use case. We want to find the scenarios that appear to be critical, to do further analysis here and gain insights in up to our ODD and also into the behavior of different agents. Now, I've already pointed out FMI as an important standard. I've pointed out OSI as an important standard for the communication between different simulation models. I've pointed out SSP, which we use to combine several FMUs in a larger network for the ego vehicle. And of course, we also used OpenDrive and OpenScenario to define the map and also the dynamic behavior in our simulation. After we have built up all of this and integrated it from the technical point of view, we were able to execute the simulation, which is shown in the bottom of the poster. On the left side, we can once again see an execution chain, which especially highlights that execution was not only done sequential, but it parallelized. We had multiple Docker containers running. In each of those containers, a single simulation was executed, and that allowed us to dramatically speed up the simulation and the time needed for the overall analysis. Now, on the right side, we can see a figure indicating the performance, and we can see that applying some sort of a heuristic here allowed us to run the simulation at around 13 instances with optimal performance here. If we do more instances, we might cause crashes on the system because of limited resources. At the same time, if we have less instances, of course, our simulation and our analysis takes much more time. So in our case, we saw that around 13 instances was some sort of the ideal point to run the simulation, and we were faster than real time with that setup. Well, and then we executed around 5,000 simulations actually, and we evaluated them. Exemplarily, we have a figure here showing the post-encroachment time, basically by how much two agents missed each other, how close it was to being a collision, or how much safety distance we had left within that simulation. And we can actually see on the x-axis the criticality. 0 criticality means that was totally relaxed, nothing special, regular traffic behavior. But we can also see that going to the right at 1, we have a peak that indicates that, oh, there is a collision. We had a simulation where there is a collision that occurred, and for sure we would have to investigate that deeper in the future. And that's how we executed a traffic simulation here. In this simulation use case, conducted a lot of different simulations based on stochastic variation. We evaluated that over more than 5,000 simulation runs, and were able to show that a simulation like this, based on agent behavior models, based on a lot of standards, to set all this up, can allow us to do modular simulations and evaluate, for example, criticality from that. Thank you very much. I'm looking forward to discussing this on other events in future with you.